So as the name suggests, today I want to talk about Eigenfunction restriction estimates on curves with non-vanishing geodesic curvatures. So first things first. So as you already know, I mean, in this talk, I mean, probably it looks like that in this session, we are interested in manifolds, but in this talk, I'm interested in a compact Riemannian manifold MG, where M is a compact Riemannian manifold without boundary, and G is the metric of N. So, okay. So here, I'm really interested in the Laplace-Beltrami operator on compact Riemannian manifold, and in local coordinates, Laplace-Beltrami operator or Laplacian for short, acting on some smooth function U is something like this. And just because the reason why this kind of the reason why we have this kind of messy expression is just because of the fact that now G is not the Euclidean metric, but it is just a general Riemannian metric. So if G is the Euclidean metric, then this expression is the same as the expression we saw in the last slides. I'm sorry, last talk. Yeah, previous talk, I should say. So in this talk, I'm really interested in the minus Laplace-Beltrami operator, specifically the eigenfunctions of the Laplace-Beltrami operator, right? I mean, okay, so in our talk, E lambda is the eigenfunctions of the Laplacian, so that minus Laplacian acting on E lambda is going to be lambda squared times E lambda, so that lambda square is the eigenvalues associated with this eigenfunctions of the Laplacian. And here, just for simplicity, let us say that this P is defined to be square root of minus Laplacian, so that P acting on E lambda is going to be lambda times E lambda. And just for simplicity as well, let's say that E lambda is L2 normalized over the full manifold. And by compactness, it is known that the set of such a lambda is discrete, so that the only one and only limit point of this set is plus infinity. Why are we interested in this kind of setting? Well, the reason why we are interested in this kind of setting is that when we apply wave operator on this type of thing, then we are going to get zero, which means that, sorry, e to the plus minus it lambda times e lambda can be thought of as a building block of the solution to the wave equation. So if we better understand the solution, if we better understand this type of building block, then we can better understand the solution to the wave equation. But we know how things are going for e to the plus minus it lambda term. So we are interested in the this type of eigenfunctions of the Laplacian. So in this talk, we are interested in the property of the LP estimate of the eigenfunctions of the Laplacian. So in this talk, let's say that gamma is a curve in manifold M and sigma is an embedded submanifold in M. And one of the difficult thing in this topic is that it is really hard to study the single eigenfunction E lambda itself. It is really hard to study itself. So now let us avoid that kind of problem so that we can say something about it. For example, how can we try to approximate the eigenfunctions of the Laplacian E lambda so that we can think about that kind of approximation or something like that. So to do so, let's say that P is equal to square root of minus Laplacian as before, and by the spectral decomposition, we can think of this P as the sum of lambda J times EJ, this kind of thing, where EJs are L to the L2 orthogonal projection operators associated with eigenvalue lambda J. And to think about the approximation for the eigenfunctions of the Laplacian E lambda, let us first think of the chi, which is a Schwarzkreis function and which is also an even function, so that chi hat, I mean Fourier transform form of chi is pointed away from the origin, and chi of 0 is equal to 1. Then we want to think about this type of approximation operator for the eigenfunctions of the Laplacian E lambda. So, okay, what does it mean by this? Well, this kind of approximation operator can be defined like this. And what does it mean by that? Well, we can just replace this P by lambda J and summing up everything where EJ here is going to be the same as EJ. So this definition is coming from the spectral decomposition of our P, which is equal to square root of minus Laplace Beltrami operator. Why are we interested in this kind of thing? Well, if we replace this F by E lambda, then we are going to get this. But the thing is, EJs are the L2 to L2 orthogonal projections to begin with, so that this is going to be vanishing. This is going to be non-vanishing, and E lambda, if and only if lambda J here is going to be the same as lambda here. So every term vanishes, but only this term remains. But okay, so this chi of 0 is coming from the case where lambda is equal to lambda J from the projection computation here. But the thing is, chi of 0 was defined to be 1 to begin with, so we are going to get this. So if we can better understand how things are going for the approximation operator, then we can think about some kind of concentration of the eigenfunctions of the Laplacian, something like this, right? I mean, if you replace this F by E lambda, then we are going to get this just because of the fact that we are thinking about the L2 normalized eigenfunctions of the Laplacian E lambda. So we want to think about this one first in this talk. And this question was already solved by Sok. And Sok said that, okay, the operator norm of the approximation operator from L to the LP is bounded over by lambda to the power delta P up to some uniform constant, which is only depending on M, which is our ambient manifold, where delta of P is expressed something like this. So this kind of estimate hold for any compact Riemannian manifold. So this kind of estimate sometimes called universal estimate, just because of the fact that this holds for any compact Riemannian manifold. And he also have shown that these estimates are sharp. Well, when they are sharp, when P, he showed that delta of P is sharp for small p's when E lambda on the unit spheres are the highest wave spherical harmonics, and delta of P is sharp for large p's when E lambda on the unit spheres are the zonal harmonics. One thing to note here in this slide is that, okay, the highest wave spherical harmonics and the zonal harmonics on the unit spheres are really concentrated on a really small portion of the unit sphere, right? I mean, the highest wave spherical harmonics are really concentrating along the great circle of the unit sphere, whereas the zonal harmonics are really concentrated on the two poles, say North Pole or South Pole of the unit sphere. So they are really concentrated on a really small portion of the unit sphere. Then the next question is that, okay, not only restrict on the small portion of the unit sphere, small portion of the manifold, but how things are going if we think about restriction to the sum manifold, not even the small portion of the manifold. That's the next question. And the next question was already solved by Borchardt and Spekov and Fu, and they already have shown that this type of approximation operator has this kind of approximation norm, right? I mean, operator norm of this approximator operator from L to the LP is bounded off by this kind of much, this kind of quantity, where delta P, delta of Kp is expressed like this, and kappas of T is expressed like this. Well, where M is the dimension of the ambient manifold M, and K is the dimension of the submanifold sigma. And these estimates are sharp except the logarithmic term here on the unit sphere, and they have shown something like this. In this talk, we are interested in the case of the hypersurface case, and fortunately, the logarithmic term here is vanishing when k is n-1 or hypersurface case. So we don't need to worry about this logarithmic term in the rest of our talk. So let us focus on k equal to n-1 case or hypersurface case. Especially, let us think about the case where k is 1 and n is 2. Then our submanifold sigma is just a curve or general curve. And by a simple computation in the previous slide, then we can see that delta 1, 2 is going to be 1/4. In other words, this operator norm is bounded off by lambda to the power 1/4 of the subuniform constant. So this is the case for every general curve on the two-dimensional manifold, compact Riemannian manifold, I should say. Okay, so in this case, we can think, so this kind of thing happens for every submanifold sigma. In this case, it is a curve, every curve. So this kind of thing is satisfied for every curve. So especially on the geodesics. So wave propagates along the geodesic. So along the geodesic, we expect more concentration for the eigenfunctions of the Laplacian usually. So the next question is that, okay, what happens if we restrict our attention to a curve which is not a geodesic? And that question is also solved by both Jordan, Chekhov, and Hu. So if M is two-dimensional manifold and gamma is not a geodesic but a curve with non-positive geodesic curvatures, then L2 to L2 operator norm of the approximation operator is bounded off by lambda to the power 1/6, which means that we can replace this 1/4 by 1/6, so we get a better bound. I mean, we have improvement in lambda for the curve with non-vanishing geodesic curvatures. And these estimates are also sharp on the unit spheres. Okay, what makes a difference? Well, if gamma is a curve with non-vanishing geodesic curvatures, then we can say this. What does it mean by that? Well, in Borg-Jordan Chekhov's paper and Hu's paper, the analysis for the Riemannian distance function on the curve gamma is going to be essential, was going to be essential in their papers. The first viewpoint there was that, okay, the Riemannian distance on the 2 points on the gamma curve is going to be expressed something like this, especially here, C of R is non-vanishing. So this is the place where they wanted to think about this assumption non-vanishing geodesic curvatures in their paper. And another viewpoint was that, okay, let us think of this gamma of S as Y in polar coordinates or geodesic polar coordinates, something like R times omega, where omega is an angular variable. So with fixed R, they thought, who thought that the canonical relation associated with the phase depending on X and omega has at most two-sided folding singularity. Okay. In general case, this C of R may be vanishing, and this canonical relations has at most one-sided folding singularity. So they are different from each other, and that makes a difference in their argument. Okay, what's next? So far, wave propagates along geodesics, so we can expect much more concentration for the geodesics. And if it is not a geodesic, then we are going to think about less concentration. So what happens if we think about chaotic curve or something like that? And that's the case where our ambient manifold M has non-positive sectional curvatures in it. So when M has non-positive sectional curvatures, then there's no conjugate points on M. So every curve there is behaving chaotic. So that's the place where maybe we can think about a better bound for the eigenfunctions of the Laplacian. And in this topic, the usual way to think about this kind of thing is to start to define t something like which is something like compatible to log lambda. So t is equal to c0 times log lambda, where c0 is positive or small but fixed. So instead of using the previous approximation operator, now let us think about a new approximation operator, chi of t times lambda minus p. Then, by the same token, chi of t times lambda minus p acting on e lambda is going to be the same as e lambda. So we want to think about this kind of thing. So usually in this topic, we want to think about TT star argument first. So in the sense of the TT star argument, we want to think about chi square of t times lambda minus p acting on f. And by a simple computation, we can think of this kind of left-hand side here as the right-hand side here. And fortunately, the contribution of the very last term is negligible, so we can ignore this kind of thing. So we can focus on this kind of thing. And usually, we can lift our problem, cosine propagator, I should say. We can lift our cosine propagator to the universal cover by using the Cartan-Hadamard theorem, and we can use the Cartan-Hadamard theorem just because of the fact that we are assuming non-positive sectional curvatures in the ambient manifold. And that's the reason why we want to assume non-positive sectional curvatures in the ambient manifold. And that was observed by Berard and Sok and Geldich. So this is what I was able to show. Okay, so let's say that MG is a compact two-dimensional smooth Riemannian manifold without boundary with non-positive sectional curvatures. And let's say that gamma has non-vanishing geodesic curvatures, then we are going to get this bound, right? Previously in Borchardt and Chebekhov's and Fu's version of this kind of thing was just lambda to the power 1/6, but I was able to get another decrease in the denominator, which is the power of log lambda. So we can get a better bound compared to the previous one if we assume the non-positive sectional curvatures in the ambient manifold. So the basic idea was there that, okay, in Borchardt and Chebekov and Fu's paper, they wanted to think about the truncation of the Riemannian distance function, or they wanted to think about the angular variable also in the sense of the canonical relation or something like that. Here, I wanted to think about the truncation of the angle in the cotangent bundle by using a pseudo differential cutoff where the symbol is supported, essentially supported, not exactly supported, but essentially supported, where absolute value of the angle is compatible to 2 to the minus j, where j is running from minus infinity to this capital J, or some fixed number to this capital J, something like this. Then by using Lux parametrics and some integration by parts argument, I was able to show this. So the rest of the thing is to think about the summation of all this kind of qj. And for some small j's, I was able to show this by using Lux parametrics and stationary phase argument and Young's inequality, so on and so forth. So the remaining part was the largest j cases. But in this case, we can think about TT star argument, and we can lift our problem from the base manifold to the universal cover we explained in a previous slide, then we are good to go. So what's next? Well, in this talk, I talked about the curve with non-vanishing geodesic curvature, say gamma, and we can think about the higher dimensional analog of this gamma, say sigma. So let's say that sigma is a hypersurface with positive or negative definite second fundamental form, so that gamma is just a lower dimensional analog of this sigma. Well, Borchardt and Chebekov and Fu was able to show this kind of thing, and what I wanted to say today was that, okay, assuming non-positive sectional curvatures, we can improve this lambda to the power 1/6 to lambda to the power 1/6 over some power of log here, but who already have shown that same bound for higher dimensional case, and we don't know how things are going for the higher dimensional case. What I talked about today was we are still working on this one, so hopefully we can prove this one later. So thank you so much for your attention.